So good evening and good afternoon for all of you. So welcome to this session. We will be having some interesting discussions, papers presented on indoor environmental quality. We have 4 topics for discussion today. So myself, Rajshekar, I am a faculty member at the Department of Architecture and Planning at IIT Roorkee, India. So cutting it short, let us move on to the first presentation. We will have Sayali, who will be discussing about indoor environmental quality issues of construction workers housing in India. So over to you, Sayali. 10 minutes. I will give you a beep a minute before.
Okay. Thank you so much. Yeah, I'll share my screen.
Yes.
I hope it's visible and I'm audible.
Yeah, it's visible, you are audible. And just for the audience, queries, as you usually do, post your queries in the QA tab. After each presentation, we will have a few minutes to discuss them with the presenters. Over to you. Thanks.
Thank you so much. Good afternoon, all the panelists and fellow researchers. I'm architect Saili Andhari, Assistant Professor at Dr. Bhanuben Nanavati College of Architecture, Pune, India. Today, I will speak about evaluating indoor environmental quality of on-site construction workers' housing through performance-based simulation. The topic of research was part of my master's thesis, and Professor Namrata Damankar, she guided me on this, and she's also co-author for this research paper. The construction industry is one of the India's largest job creators, and the infrastructure projects that lead to cities' growth and development create jobs for migrant workers. A construction worker is the most integral part of the construction sector, but it is but they are the most vulnerable and often neglected. We have seen significant development in the architectural world, from tiny shacks to high-rise buildings. However, the living conditions of these construction workers have not changed at all. In addition to the minimum wages, overtime pay, and weekly offs, the migrant construction workers should be provided with comfortable housing as per the Building and Other Construction Workers Act 1996. As a result, it is a developer's responsibility to ensure that the working conditions of these construction workers should be improved, and they should be provided with good quality of housing units. But the sites of these construction workers are rapidly changing, and that's why the developer end up giving them temporary shelters, which have very basic facilities, and in turn jeopardize the comfort of these construction workers. Also, giving them a permanent solution is not viable to these developers, because financially it doesn't work out for them. So the big question here is whether this growth is benefiting the standard of living of these migrant construction workers, and what can be done for it. The research explores the possibility of providing a holistic solution for constructing housing system for on-site construction workers, the on-site life-scale prototype building, and testing for indoor environmental parameters and users' feedback for assurance of workability of the proposed system. The findings are also relevant in developing countries where construction workers are important development stakeholders. Along with construction workers, it will also assist the builders to provide a proper system to meet necessary health and safety criteria for the construction workers. The key innovations in this research is basically a modular system for on-site construction workers, practical implications of the system, wall paneling system for thermal insulation and better indoor quality. Also, use of eco-cooler system. Basically, it's a passive.
Sayali, sorry to interrupt. Can you speak a little slowly, because
sure.
Following the thing becomes a little difficult.
No problem. I'll go slow.
Just the pacing, yeah.
Yeah, the timing is such that I have to cover a lot of things. So
no problem, but just focus on the results. Maybe go a little low pace.
Sure, no problem. Thank you so much. So basically, the research is focusing on the possibilities of providing holistic housing solution for on-site construction workers, and the key innovations in this is modular system, practical implications of this system. Wall paneling is one of the important aspects to achieve better indoor quality, and use of eco-cooler system, which is a passive strategy to achieve indoor thermal comfort. Now, the methodology has developed in such a way that an approach was developed that combined interviews, case studies, observations, content analysis, and in addition to this, a customer satisfaction survey was also conducted, gaining through a grasp of housing options and user comfort for on-site construction workers. So it was done through interviews of developers as well as the users. the existing literature has provided an understanding of indoor air quality issues and how simulation can be utilized to analyze the current situation and assist in designing an environmentally friendly residential unit for on-site construction workers. So the importance of indoor environmental quality cannot be overstated because it affects people's health in long term as well as in short term. Thermal comfort, ventilation, humidity, and daylight contributes to the definition of indoor environmental quality. Thermal sensation index values of 25 degrees to 30 degrees are basically comfortable, and something between 30 degrees to 34 degrees Celsius is tolerable, but something which is beyond that is not tolerable. Also, in hot and humid climates, ventilation is one of the important aspects to achieve thermal comfort. And most important is one of the factors is the material which is used for the envelope. So the material of which the building is constructed determines the relationship between the outdoor temperature, solar radiation, indoor temperature. And specifically, this is applicable in a non-air conditioned building. And most of the construction workers units, they are all non-conditioned, non-air conditioned. That's why these are very important criteria if you want to build a unit which is comfortable for the users. So a design approach was basically developed. The challenges and pitfalls of the existing workers' housing were examined. Analysis indicates that the large metal pipes were used as structural elements. Corrugated metal sheets were used for the walls and roofings, that is basically for the envelope. And there were no windows provided in the existing unit. Also, it was poorly ventilated, complete lack of ventilation and light. And basically, because of the material choice of materials, there was a lot of heat gain, and the indoor spaces were not very comfortable for the user. So these were the observations, on-site observations, and also some studies from the literature review. So an approach was developed where the focus was given to the comfort of the user, adaptable spaces, versatile unit was provided. And to achieve this goals, basically two criteria were used. One is the selection of the materials, and second is the parameters which define the system. So for the selection of the materials, durability, low cost, local materials, healthy materials, that is comfort giving materials were selected. While for the systems, basically a system which should be sturdy, reusable, transportable, modular, lightweight, additive, fireproof, and waterproof. So these were the criteria for selection of the materials and the system. So so the research was basically an experimental research, and a lot of material exploration was done for the envelope, where actual wall assemblies were tried, tested for different aspects. Comparative analysis between different materials was conducted. That was for cost of the material, durability of the material, strength of the material, U value, which defines the heat gain, moisture resistance, fire resistant, also the standard size. So these were some criteria to decide the materials, and the analysis were done for wall panels also, as well as for the roof system. And based on that analysis, a new system or the new material palette was proposed, which basically had hollow box sections, paper honeycomb board, sandwich panel. Now here paper honeycomb board has been used because paper honeycomb board has a lot of air cavities which provides thermal insulation, and it was sandwiched between GI sheet to achieve fire resistance and moisture resistance. Then 12 mm thick cement sheet was used for the flooring. GI sheet was used for the roofing, but at the same time, aluminum bubble wrap was added for the insulation purpose. Now in the base case, that is the building as usual building case, basically that there were no windows. So here we have added windows also in the proposed system, along with a passive strategy that is called as eco cooler, where we have used PET bottles, or let's say we have used plastic bottles, we have reused them, and it was done in such a way that the bottles are chopped and used as a window panel, where the air is compressed and released inside, which eventually reduces the temperature, which is called as a Bernoulli effect, which has been effectively used in the proposed unit. Now, the system has been designed in such a way that it's a DIY kit. So the whole unit can be built in 2 to 3 days. And basically, there are 3 processes involved. One is manufacturing offsite, then packaging and transporting, and lastly, installation of the whole unit on site. So the system is developed in such a way that we are not disturbing the ground, and it can be taken from A place to B place very easily. So we have bucket foundations here. Step 1, we lay the bucket foundation. Step 2 is we lay, make the assembly of the main frame. Then we add intermediate members. Then we add the envelope, which is the prefabricated panels of honeycomb sandwich GI sheet panels. And then we also add windows and doors over here along with the eco cooler. And eventually, lastly, we add the roofing material. So if in this, we can see a quick assembly of the unit. And on the right hand side, what you see is the actual unit which is built on the site. So the proposed unit, what we have planned, that is actually built on the site for its thermal performance, checking of the thermal performance and feasibility. So simulation was the most important part of this research, and simulation for the daylight was done, simulation for energy was done, as well as simulation for ventilation was also conducted in this through this research. So we can see that in the building as usual case, there is absolutely no light because the windows are not provided. While in a design case or the proposed case, we have added windows and we have also added vents. So by adding windows, basically we are able to achieve better quality of light. Now in this case, the unit will be mostly used at the night time, but in the daytime, whenever it is used, at least we have desired lighting condition in the housing unit. So we can get 100 to 300 lux of light in this unit. And we have, instead of glass, we have provided polycarbonate sheets because modularity is one of the important aspects which we have considered. That's why we have used polycarbonate sheets in the proposed system. Also, if we see energy, so for energy, we have used Design Builder as the simulation software, and temperature, humidity measurements were taken for both base case and for design case. And we can see that we have achieved reduction in the electric consumption. We have also reduced the discomfort hours, and we have also reduced the temperatures. So basically, if we see EPIs, we have for the building as usual case, we have 31 kilowatts meter square, while in the design case we have 19. So we can see definitely reduction in the EPI also. Also discomfort hours are less, but if we compare the two, the difference is not much because we have tried to simulate the actual case. So in the existing case, the base case.
Sayali, you have another minute left.
Sure. Yeah. So discomfort hours we could not reduce because of the existing condition, and in the existing condition, the unit is shaded from all the sides, while the proposed unit is built in such a way that it is exposed from all the sides. Probably that is one of the reasons why we have achieved less reduction in the discomfort hours. We have also done analysis for ventilation and thermal comfort. We have done airflow analysis. We have also done CFD analysis. And through that, we can see that by using eco cooler, we could get reduction in the temperature. So whatever is outdoor temperature and what is inside, we could get reduction of 1 degrees. Also, we could see that because of providing of windows, we get very good ventilation. Also, U values have been reduced by using thick panels of honeycomb board. So honeycomb board has helped to achieve lesser U value for the proposed system. The thickness of the paneling is 35 mm, which helped me to reduce the overall heat gain. And lastly, my finding says that the simulation helped a lot to understand the existing scenario, and also it helped to design the proposed case in such a way that we can achieve thermal comfort. So we can definitely say that in existing condition, there was lack of ventilation and the envelope was such that there was a lot of heat gain. So in proposed condition, by using simulation as one of the tools and also CFD analysis, we could achieve better environmental comfort and better thermal comfort for the users. There is a lot of scope for future research because we can explore the wall paneling system, we can explore various thicknesses. That is one of the key things which we can explore in the future research. Also, right now, the research was done for a particular time and a particular time zone. So it was only conducted for warm and humid climate. So we can conduct this research for all the climate types. Also, it can be done for year-long time frame. Right now, it was done for a very small, short span of time. So it can be done for a year. That is one thing which can be again done for future. And also more investigation on the eco coolers and its performance can be done. So basically, simulation as a tool help us to understand a lot of things, and definitely it can be taken further for future research. Thank you so much.
Thanks, Sayali. That was, very impressive piece of work. I don't see any QA from the audience side yet. I have a couple of things to check. You did build an actual prototype, right?
Yes, we
did.
This
was also part of your work. So
yes.
Did you attempt to measure anything in this
yes.
unit?
Yeah, so what we did is after building it, we installed it on site and we did on-site data loggers we have used, and we have used temperature and humidity measurements we have taken on site. And we did it for almost continuous 1 month, 2 months we have done that. 2 months data log, and we could see that there is a reduction in the temperature as well as in the reduction in the heat gain because of the paneling system which we have developed. So honeycomb boards have really worked very well here because it has air cavities, and the material itself is a reusable system. So what the whole idea is that whatever materials we use, they can be reused multiple times, and it should be affordable also. At the same time, we should be able to achieve thermal comfort. So that way, using honeycomb board, we achieve the affordability. At the same time, thermal comfort was also, heat gain was reduced, and discomfort hours was also less compared to the base case.
Just a piece of suggestion on that to add. I don't think we should be worried about EPI in this case, because here we are talking about, say something like a health ventilation, not comfort ventilation. We are talking
Right.
about well-being, not energy saving. So
Right.
technically, you are kind of improving the life safety of people,
Yes. Yes. I
rather,
understand. Yeah.
minimizing risk. So, I mean, it is very interesting. At least I'm happy to see you have a actual building standing out there.
And
What could have been
actually,
even more? Yeah, go ahead.
sorry, just to add that we actually asked users to stay in the building itself. So the unit, users actually used it, and they say that, by adding eco cooler or by adding windows, the quality of life is improved. Also, the visual quality of life. One is the thermal comfort, but otherwise visual comfort also. The way they live in the patra houses or the GI sheets, it's very bad. And they say visually also it is comfortable and it is comfort giving. Overall, the unit is comfort giving was the feedback from the users also.
Did you try documenting it, publishing it separately elsewhere?
It's in process. I'm working on it,
Okay.
and I'm actually now
Because more
going
than
to.
simulations, because you have a building right there, it would be
Right.
much more impactful if you are really documenting the performance plus people and their feedback. Okay. Thank you.
Yes.
Thanks,
Thank you.
Sayali. It is very
Thank
interesting work.
thank you so much.
We move on to the next paper, take you to the other side of the globe. From Peru, the impact of built environment on thermal comfort in informal settlements. So I think it is a recorded presentation. We have Marion with us. So Callum, you can play the video.
Good morning, everyone. I'm Marion Verdière, an architect from the PUC University in Lima. Before presenting the following research in detail, I wanted to highlight that all of the work that I'm going to present was developed during the pandemic, which forced us to adapt a lot, working hand in hand with the local assistance and the population. This research is part of GEMDEV project, which aims to analyze and propose improvement in access to housing and energy in informal settlements in Lima, Peru, and Ahmedabad in India. There are 4 work packages that guide this investigation. The first one is focusing on governance and planning processes in terms of energy and housing. The second one is about the daily practices of the inhabitants in terms of energy access and consumption, and in their influence on the comfort of the home and the space used. The third work package in which this article is focused in providing data on the thermal performance of the housing archetypes and their ability to provide comfort. With this modeling and simulation, it will be possible to propose improvements in housing and arrive at proposals for archetypes capable of providing thermal comfort in marginal neighborhood. It's work package 4. Here, I am going to present the first scope of the study halfway through the investigation in one of the 3 study neighborhoods. Building energy simulation is little used in Lima, whereas the generally mild climate means little energy is used for space heating and cooling. This study is the first attempt to explore thermal comfort for marginalized communities living in self-built accommodation. The geography of the Peruvian capital influenced the urban organization we can see on the map, where the oldest urbanization is represented in yellow and the most recent in red, here and here. This last urbanization come to settle in the valley of the Andes, represented there in a more intense gray color depending on the heights, here. In the case of this article, we are interested in José Carlos Mariátegui, here. Neighborhood located in the desert hill on the outskirts of Lima, results of the successive invasion, as you can see in the photos that show the evolution from the 80s to the present. We have defined 3 housing archetypes that correspond to the evolution of housing according to the improvement in the quality of life of the inhabitants over the year. In this photo, you can see a house where the inhabitants live in very precarious dwelling made of lightweight materials, generally composed of walls of wooden boards. We call the archetypes the lightweight archetypes. In the second photos, you can see the evolution of the on the photos, where the roof is equally light, usually corrugated sheets of metal or fiber cement, and the walls are gradually replaced with walls of brick, providing increased thermal mass to the envelope. We call it the intermediate archetype. The third archetype that you can see on the right in this image is with a reinforced concrete slab lightened with hollow bricks with the idea of acquiring more safety and comfort. This is a substantial archetype. In this case of the third archetype, families have the habit of continuing to build more floors, up to 4 or 5 with the same technique, and sometimes with the last floor made of light material, as we saw in the lightweight archetypes. With the idea of exploring thermal comfort in this type of housing through the look of the construction materials used in this marginalized neighborhood, we've installed a meteorological station and 15 data loggers in 3 archetypes. It's important to emphasize that the study was carried out in pandemic situation, as I said, which complicated the creation of a bond of trust with the population, who on some occasions expressed distrust of the measuring device, for which we have worked hand in hand with the local assistants who were able to carry out the installation of the data logger and the development of the survey. Here you can see in the graph with preliminary results of the external climate condition record, the results were quite predictable, around 1 degree below normal. The 2-week period that are represented, the representative of the hottest and the coldest time. Here, the hottest one in March, here the coldest one in June, with all of the detail of the temperature, the humidity, the relative humidity, and the solar radiation. In this graph, you can see the interior conditions in the house valued according to the recorded operating temperature. We can clearly see that the material is decisive in the thermal behavior of the house. Despite the fact that all the parameters that influence the interior condition are not represented here, such as ventilation or orientation. Except for a house of the intermediate archetype that is very hot in summer and a house of the substantial archetype that is very cold in winters, the correlation between the construction materials and the indoor temperature condition can be found. Also, it can be noted that the average temperatures are very similar regardless of the material. In this graph, you can see the solar radiation and average temperatures in winter and summer according to the different archetypes. It's clearly seen how the light archetypes follow the outside temperatures, both in winter and summer, here and here. And being slightly higher at night and notably higher around noon. Regarding the comfort zone, here and here, you can see condition of excessive heat in summer here, about 24% of the time, and uncomfortable in winter here, almost 30% of the time. This pattern is repeated with less intensity for the intermediate archetype here and here, sorry. In the case of the substantial archetype, great thermal stability is noted, which makes it possible to maintain a practically permanent stability. This one and this one. Even though certain conditioning factors that influence the thermal performance of a building, such as ventilation or solar incidence, again, have not been considered, the individual result of the dwelling have coincided according to the archetypes, which shows that the construction materials is decisive in the thermal results. The very high temperatures that are reached in summer in the lighter archetype are striking, around 34 degrees inside, even above 40 degrees in some cases, and between 5 degrees and 10 degrees above the average outside temperature, which reveals the low level of insulation and thermal inertia of the materials and the ineffective natural ventilation in the face of high solar radiation. In the case of winter, for a large part of the day, the interior conditions are not comfortable, 15 hours between 6 in the evening and 9 in the morning. Once again, evidencing the low level of thermal insulation, the low mass, and a high infiltration level. As first conclusions, looking at the identified archetypes, it's possible to verify the hypothesis that with relatively low thermal insulation values and with an intermediate thermal mass in walls and ceiling, comfort conditions are guaranteed in an apparently moderate climate like Lima. For this reason, it's very important to take into account the traditional architecture of the pre-Hispanic and colonial periods that precisely use adobe or mud that have high thermal inertia and are themselves very adapted to the Lima climate. Besides, we also observe that the objective of low-income family is to build a noble material house, which is constituted of bricks and concrete. It's understood by issues of social recognition and also security against theft or fire. This type of construction also offers families the possibility of continuing to build vertically and thus increases the size of the home to accommodate all family members independently or generate a profit by renting the spaces. The first finding of this allows us to observe that the solution will also provide thermal comfort to its inhabitants. However, it's very expensive for the member of the community, and bricks and concrete have significant environmental impacts and are difficult to transport to the highest place of the hill that do not have access for cars. There are some of the reasons why its automatic use has to be questioned. The next phase of this study will involve completion of data collection in José Carlos Mariátegui and 2 other informal settlements in Lima. This data will be incorporated into community-scale building energy models to allow the evaluation of a range of intervention to improve thermal comfort. The ultimate objective being to identify specific strategies which can be employed by communities to improve living conditions in existing and future homes. Thank you very much. If there is some question, please let me know. Thank you.
Thank you, Marian. That was an interesting work. I have a couple of points to discuss. I don't see a question yet on the QA box, but I have a couple of points to discuss other than question. Did you have any comparison for the formal settlements in or around that locality? Because you did mention about the colonial and Spanish time period settlements.
Yes, in the 3 settlements you are studying, one of the 3 is an oldest one with this kind of walls of this material, but let's see that the formal settlement will be really interesting to study too, because we can have a lots of data to, but for this investigation we are focused on this one, José Carlos Mariátegui, that I presented. Another one, Barrios Altos, it's in the historic center of Lima, and it's with this kind of wall with earth. And another one, it's the name of El Agustino. It's like José Carlos Mariátegui, but older, because it's from the 50s, and José Carlos Mariátegui is from the 90s. So with El Agustino, we can imagine, we can see how José Carlos Mariátegui will be evolving, and we are doing this work. But the first result we have in this settlement, we are waiting for the other two more.
It's a commendable thing, especially in the pandemic period. I can understand the difficulties in field work.
Yes.
That is, I also think there will be a lot of trade-off with disaster resilience, right? There are other issues like landslides.
Yes.
Natural disasters.
Yes, in Lima, the first issue is not the comfort. That's why we don't have a lot of investigation about this. People are thinking about earthquake a lot because we are waiting for a big one, and people are aware about this. About comfort, it's like a new issue for them. When we are speaking with the people, it's like, no, I'm okay. I can live like this. Now I just want a house more secure and safety house. Yes, it's this kind of preoccupation, but we are thinking about how we can connect the comfort idea with the health, because it's true here people are sick because of the humidity, because of the kind of winter we have, and the material of the house don't help to the people to have a better health. So we are trying to connect this kind of big issues together to make sure that people can take this problem with a little more interest.
Thank you, Marian. That was very informative. Thanks. So with this, we move on to the third presentation. Again, I guess it is a recorded presentation. Siddhej is here. So the paper is about impact of green building on productivity of offices, productivity in offices. So Callum, you can go ahead.
Good afternoon, everyone. A warm welcome to you. So today I'll be discussing the impact of green building on productivity of offices. This is Shatish Kakkad, and right now I'm pursuing my PhD in IIT Roorkee, India. So productivity is the ability of a person to enhance their work output. It can be done by increasing the quantity or quality of the product, or both, or the service which is being delivered. By increasing the productivity of an employee, it may lead to a reduced operational cost and an increased profitability. Many of the researchers like GRIHA, IGBC and all green indices claim that sustainable and green building help to increase the productivity of an employee in a workplace. But there is no proof that maximum comfort leads to maximum productivity. There is ample evidence to show that it leads to improved health environment and decrease in workers' complaint and absenteeism. So which means that indirectly it is enhancing the productivity. In many white-collar jobs, the largest expense that an organization pays is the cost given to the staff, which is the 82% of the whole cost being paid. So a relatively small investment in building design and operation may lead to a relatively big benefit on the productivity. As humans spend most of their time indoors, majority of the work population live in urban areas and majority of them work in an office environment. In plus addition to that, the service sector is a key driver of India's economic growth. So we have to see that the importance to understand the indoor office environment and the effect it has on occupants' productivity is of high importance right now. Office environment has a higher level of influence on occupants' productivity as seen by many researchers, and the past study on sustainable design also show that green design strategies and technologies may enhance the indoor workplace environment. Cumulatively, we can see that there is a need to investigate the quality of the indoor workplace environment and its relation to the occupants' productivity. The lack which is being present in these type of studies is that these green building certifications do not address this aspect of productivity, but the claim is being made that they can improve it. For example, LEED green building rating system has indoor environment quality category in it, which focus on thermal comfort, indoor air quality, lighting, day lighting, quality of views, acoustic performance, etc. This gives us the opportunity to analyze the indoor environment quality criteria and various international green building guidelines that are present over there. To understand the effects, we need to first understand various aspects of productivity. So it can be a social aspect, an organizational aspect, an environment aspect, or personal aspect. Data collection in all of these aspects becomes very difficult, but evidence show that the environmental factor have a indirectly connection and improvement towards the productivity of a workplace. So when we talk about productivity, it's basically an hypothetical construct and cannot be directly measured, but it can be estimated through performance indicators and other criteria. We can use the concept of subjective productivity measurement, which is based on our own personal aspect rather than absolute quantitative values, and this can be done through survey questionnaire. The modern office buildings have these problems that IEQ calculations is becoming a challenge as the inputs and outputs are not clear. So self-assessed measure is considered a better approach than having nothing in your hand. To understand what is being to be done, we made this methodology chart, which shows that the first parameters are to be shortlisted or based on productivity in green building rating systems that are present, for example, in IEQ parameters, and the other researches which shows that these are the parameters that in a building design and environment that affect the productivity of an employee. Other than that, tool for data collection and data analysis were to be shortlisted. After this literature, a questionnaire type of data collection method was shortlisted, and this was a weighted type of questionnaire for collection of data other than that of the employees' self-assessment. Various instruments were used to see what is the real-time conditions they are working in. Then through this data, an equation through multiple linear regression was generated, which was validated for 2 of the case studies. Once the equation was validated, it was being used for green building data and for a conventional building data, so see the comparison between them. Through various literature reviews, parameters like the temperature, acoustic comfort and noise, indoor air quality and ventilation, etc. shown on the left hand table came out to be known. On the right, you can see that the LEED certification contains indoor environment quality parameters like indoor air quality, thermal comfort, lighting, acoustic as parameters. Through both of these tables, the common factors were being shortlisted, so which were indoor air quality, temperature, humidity, lighting, acoustics, and office layout. The area boundary that was being considered was the composite climate zone according to the National Building Code of India 2016, and in that also architectural offices were being considered in Lucknow, that is the capital of Uttar Pradesh, and New Delhi, capital of India. The reason for this area limitation was that external climate conditions may have an effect on the IEQ, which lead to skewness in the data. For example, a person staying in a high humid region has 80% humidity right now, to which he or she is acclimatized. But the same person, when he lives in a drier area, for him the 80% humidity is very much. So body gets acclimatized to these conditions. So places with same weather condition and similar workplace were being considered. Workplace is also said because the person working in a bank will have a different perception or requirements than a person working in an architectural office, than a person working in mine, than a person working in another institute areas. Data collection was done by various instruments that contained lux meter, decibel meter, IEQ meter, anemometer, etc. And the values were taken in decibels, degrees Celsius, lux, etc. The office layout values were taken into binary considerations like 0 or 1. For example, planning, if an open plan then 0, if a closed plan then 1. Similarly for other spaces. Tools that were used like Prana Air's Care Plus meter, which calculated the AIQ levels, temperature, humidity, CO2 levels, etc. Digital lux meters were used, certified anemometers were used, apps that can tell you good decibel values were being used. The questionnaire was divided into two parts. The first part was to provide the weightages to various parameters, and the second part was to mark the quality of factors or parameters in which the employee is working. So this weightage and scores were being multiplied to come out to the final value. So in the pilot study, a case test 1 was taken, which was for a bank in Lucknow. The parameters were calculated and the survey was done. So it came into consideration that the employees' answers were showing a low productivity than that in an architectural office of the same type. So the reason that came was that the employees of an architectural office can understand more better these terms of acoustics, temperature and all, and they could give more reliable inputs to the survey question. So now the study was focused only to the architect's office, and these are the parameters of the first case study, and this is the survey questionnaire, which was at the end averaged out for each office. Similarly, 15 offices were taken, total having a respond value of 132 employees. After removing all the skewed data and outputs, the cumulative table is being shown over here on which the regression was being. So firstly, a simple linear regression model was run to see if each of the parameter has an impact on the productivity directly. So R-square adjusted value on the left hand table can show that all of the parameters contain a very low type of relationship while depicting the data. A 40% was shown by TOSC, but still it was less. Then a multiple linear regression was done with all of the parameters that were present, but still the results were not very good in terms of R square adjusted values. So basically parameters were at the end taken that were giving the best fit to the scattered plotted data that we had. So the R square adjusted value came out to be 78.27%, which is quite good for further calculations to go on. And the parameters shortlisted were acoustic, temperature, lighting level, AQI and humidity. You can see that acoustic is showing a positive effect. So, but we know that when the noise levels go much higher, then it lead to disturbances, and type of noise may lead to disturbance. So the equation is basically running till a value of 67.6 decibel. So anything more than that we should not be considered in this equation, because this is the threshold value up to which the data is being taken. Other than that might be after once the value goes above 68 decibel and on, the graph may show some different kind of property. So that's why we need to work within these given limits. Similarly, the temperature, lighting, AQI and humidity values are being discussed. The model was validated by using the parameters that were being calculated in 14th and 15th office, and once the calculation was done, it was compared with the productivity given through the questionnaire survey, and it was seen that the output show difference in the tolerance level. So the equation came out to be fit for use for other type of offices, for other buildings and all. So now a green building and a conventional building were being compared. So the values of were inputted for the acoustic, temperature, etc. And it came out that productivity of an office space in a green building is 38.96% higher than that in the conventional building. We can see that green building showed a 38.96% of improvement over conventional building. So the indoor environment quality parameters showed some better results. But these values are not the overall productivity of the employees. These values are relative value to understand the impact that the IEQ have on the productivity of the employee. This increase of 38.96% is due to a single case and it may vary from building to building. LEED certificate is able to show a positive result, But other parameters like color, biophilia, view, furniture, privacy, cleanliness should be considered and are important. That can affect the productivity of a workplace and should be considered as marking criteria if the certifications have to claim that their certifications can improve the productivity level. In future study, we can focus upon the sensitivity of these parameters and how the changes in these parameters can lead to a better productivity. So the overall study shows that IEQ parameters do impact the productivity of the workplace, and the green buildings as have a better set of parameters help in improvement of the productivity than a conventional building. Thank you so much. These are some list of references.
Kshitij, just a couple of points for you. Maybe if we had a glimpse of these buildings, for a broader
Yes.
audience, see, we have people from across countries. So, I mean, within this session as well as the readership. So, it would have been better to see at least some visuals of these buildings, so to make a sense of what, better and not so better building we are talking about. Just, few suggestions. I think if we are taking parameters across, for example, acoustics versus lighting versus, air quality and so on, we need to normalize the data for, when you're putting all of them together. So maybe that, weighting plus the positive negative sign issues may get resolved if you are bringing
Getting it,
everything
sir.
in a normalized fashion.
Normalized fashion.
That I see is a bit of missing link which
Okay,
to
sir.
point out. But otherwise, need for getting in this direction is pretty much there. So thanks, Kshitij. So
Thank you, sir.
with this, we move on to the last paper in this session, quantifying the effect of roof insulation on indoor comfort and cooling loads in Nigerian residences. I guess we have Henry in the session. So Callum, we can play the presentation.
Good day. My name is Henry Gugu. I'm a doctoral candidate and part-time lecturer at the Department of Architecture and Industrial Design, Tshwane University of Technology, South Africa. My current research is in energy performance discrepancies. I'm glad to be here at the BSO conference. Thank you. Welcome to the presentation of the paper titled Quantifying the Effect of Roof Insulation on Indoor Comfort and Cooling Loads in Nigerian Residences. The content for today will cover in the introduction the context of the study, and in the methods we will look at how the building geometry was selected for the study, the simulation and zoning data that were used, and the materials that were tested in this study. The results will also be discussed, and we will conclude as well as acknowledge the supports that were received during the period of the study. Nigeria's residential sector has been projected to account for 60% of the country's energy consumption between the years 2013 and 2030. The external conditions strongly suggest that cooling is the most significant need. Occupants often use air conditioners to achieve their desired indoor thermal conditions, and this can account for as much as 75% of a residence's total energy consumption. Now, considering the projected population growth from 209 million in 2020 to nearly double at 400 million by 2050, it can be argued that energy consumption in the country would increase dramatically. In addition to that, the expected urban residential energy consumption has been projected to also experience a 100% increase. These statistics define the need to urgently ensure energy efficiency in the residential sector by limiting and reducing the energy that is being consumed by cooling activities. The context for this study is Nigeria's megacity, Lagos. Current population sits at over 20 million people and has been projected to reach between 61 million and 100 million residents by the year 2100. Nearly every Lagos resident currently relies on some form of mechanical ventilation for the desired indoor thermal comfort. This presents several challenges, which includes the increasing energy consumption in the region, as well as opportunities to ensure the sustainability and energy efficiency of the built environment. In this study, roof insulation was investigated as a passive technique to aid the achieving of the desired indoor conditions while also reducing reliance on air conditioners, which will then of course lead to reduction in total energy consumption. Dynamic simulations were conducted in Design Builder to quantify the impact of roof insulation on indoor conditions as well as the total cooling loads. In order to do this, the study was phased in 5 steps. The first part was to define the building geometry, and that will be discussed in this presentation, as well as then select the simulation and design data that would be used. Of course, the roof insulation materials that will be tested were also selected based on set out criteria. The simulations were run and then the results were analyzed. The building geometry that was used in this study during the dynamic simulations was the product of 2 studies and the typical floor plan of residential typology as depicted in those studies. The first was a study by Ezema et al., which included over 10,000 residencies in Lagos. The second was by Solid Green Consulting during the generation of Nigeria's building energy efficiency codes. Now, this is the typical floor plan that was included as typical for Nigeria. Figure 3 shows the internal zoning in Design Builder that was achieved. All the spaces were zoned, however, only the habitable spaces were included in the dynamic simulations. To your right, table 1 shows a comparison of the U values for the building envelope. The values used in this study were compared with 3 other studies to improve the reliability in the building model. To test the performance of the roof insulation materials, 3 different materials were selected, namely extruded polystyrene, glass wool, and spray polyurethane foam. The selections were based on several criteria, 2 of which are significant. One is a minimum R value of 2.5 at a depth of 100 millimeters, and then second was the variance in their construction technique. Table 2 shows the material properties, which includes their thermal conductivity, the achieved R value for each of those materials at 100 millimeter depth, their specific heat capacity, and the density of the materials. The first dynamic simulations were conducted to establish a baseline. The baseline roof, which is the roof without any form of insulation, resulted in an R value of 0.418 meters square Kelvin per watts. To achieve an average annual indoor operative temperature of approximately 23.4 degrees Celsius, a cooling load of about 39,000 kilowatt hours per year was required. When extruded polystyrene was included as roof insulation in the roof construct, the total R value of the roof increased to 3.359 meters square Kelvin per watts. The observed indoor operative temperature was 23.3 degrees Celsius on an average, and a cooling load savings of 7.35% was observed. The second insulation material that was tested was glass wool. When glass wool was included, the R value was 2.982 meters square Kelvin per watt, which is a bit lower than what was observed with extruded polystyrene. The operative temperature was similar at 23.3 degrees Celsius, and a cooling load savings of approximately 7% was also observed. Spray polyurethane foam was the final roof insulation material that was tested. This showed the highest R value at 4.823 meters square Kelvin per watt at a similar average operative temperature of 23.3 degrees Celsius. The cooling load that was observed was the highest among all 3 at 8.2%. To summarize the findings of the study, the key performance indices are shown and compared in figure 12. We see the baseline value of 262.6 kilowatt hours per meter square per year as compared to the three different roof insulation materials. Again, SPF showed the largest savings, while that was followed by extruded polystyrene and then glass wool. To conclude this presentation, a few points need to be stated. Firstly, despite the considerable range in the R values for the roof insulation materials, the resulting KPIs were closely valued. Secondly, Nigeria's Building Energy Efficiency Code recommends a minimum R value for roof insulation of 1.25 meters square Kelvin per watt. This study adopted a minimum value that was double the recommended value in the energy regulations, and yet only savings of 7% to 8% was observed. Thirdly, R values beyond 3.0 meters square Kelvin per watt were observed to not show a direct increase in performance. Now, these 2 points then suggest that a minimum R value range between 2.5 meters square Kelvin to 3.0 meters square Kelvin per watt is more desirable. Fourthly, the study's findings were focused on multifamily apartments and, of course, the top floor where the roof insulation material would be, and that was used as the case study. However, single-story buildings still make up a large percent of Lagos's residential stock. Therefore, it can be stated that the findings in this study would be applicable for retrofitting purposes as well. Lastly, in line with the theme for this conference, which is building simulation and optimization, Nigeria has an urgent need for simulation metrics to be created, as well as modeling conditions for different microclimatic regions. Now, this will help aid and facilitate the adoption of building simulation and optimization practices by professionals in the built environment industry. These are crucial points which this study concludes with. The authors would like to acknowledge South Africa's National Research Foundation for the financial support that was provided during the course of the study, as well as the assistance that came from the Department of Architecture and Industrial Design, Pune University of Technology. Thank you very much for your time and attention during this presentation.
Thank you, Henry. That was interesting, piece of work. Couple of, thoughts from my side. As you said, you are focusing on the top floor in the multi-story building. I had that as a query, but you did mention towards the end of your presentation. Are you, also considering the variations in the roof material, base material? Are they all?
Okay.
You are talking about insulating it, right? So what is the base material?
The base material of the roof insulation.
No, roof itself. Is it a concrete roof? Is it a GI sheet roof? What sort of?
Okay, all of that is stated in the paper, in the full paper. But you're having essentially a tiled pitched roof, about 28 degrees pitch. It's tiled, and then underneath there is no insulation. And of course, you'll have the air gap, and then let's say like a gypsum board ceiling.
Okay. So that is one reason why probably your R values beyond certain numbers are not paying you back, I believe.
Yes. So I mean, like you saw, the baseline value was about 0.418, and then by the time you then add different roof insulation materials, for example, with the SPF, it was the largest, and it was over 4.4. It was about 4.4. But when you compare that with the other R values for the other roof insulation materials, and you see that the improvement is only between 7% and 8%. It's less than 1%, even for that dramatic increase in the roof insulation value. Hence why the study is suggesting that beyond 3.0, you start to get a diminishing return.
Okay. The last thing I wanted to ask, while you simulated, you are considering all these buildings as air conditioned, or maybe if I missed your statement on that, you can clarify.
All right, so thank you. So in Lagos, as you saw in one of the images, it's densely packed. So currently, the Lagos is about 3,577 square kilometers, right, in land area. And you have over 20 million people living in that. Okay, so you have a lot of densely packed buildings. So as you saw, studies have shown that up to 99%, which is nearly everyone, has to use some form of air conditioning to achieve that indoor comfort. I've also lived in Lagos and I've experienced that you do need air conditioning in there. So that's the assumption. But of course, in the study, we only accounted for the habitable spaces. So other zones were excluded.
What sort of air, I mean, this is out of the paper's content itself. What sort of air conditioners do they have? Do you have in place? Is it like a window air conditioning system, or what do you use?
So previously, this is a lot of years ago, we used to have the window, but now it's mostly the split air conditioning system.
Okay.
So just the unitary split, because many of the houses don't have like a central or fully fitted HVAC sort of system. It's always on an individual, family unit.
Rooms are conditioned
as well.
Okay.
So we have accounted for that as well and stated that again in the full paper. I tried to be concise in the presentation as well,
Makes
but all of
sense.
that is also stated in the methodology section. Yes.
Makes sense, Henry. Thank you. Thanks for the presentation. So here we can conclude this session. We had 4 interesting pieces of work presented. Sayali showed us, full scale building model which was constructed for construction workers. Then we saw Marian presenting about, informal settlements of Peru, challenging work. Then we had Kshitij addressing some, interesting dimension of productivity. And we had Henry talking about improving comfort in Nigerian residences. So interesting session. Thanks for presenting. Thanks for being here. So look forward to seeing you sometime. Thanks, Callum, thanks, Callum, for the support. So we can conclude the session. Thank you.
Thank you very much.
Thank you.
Thank you so much.